We have Chapter 5, Problem 8. We have here is a car going around in a circle, so we're supposed to figure out how large must the coefficient of static friction be between the tires and the road if the car going around is traveling on a level road and it's going around a curve with a radius of 125 meters and the car is traveling at 95 kilometers per hour. As usual, let's start off with a picture. In fact, we should probably draw two, one from the top and one from the side. So the top view, let's see how good this circle comes out. I've done worse. It's got a certain radius, let's call that R, and the car, which will make it tiny, kind of traveling around with some constant speed, V, which is 95 kilometers per hour. I have a suspicion that those units are not useful. R is 125 meters. Okay, and from the side, this looks like is, let's go ahead and denote this as the center of the circle. The car is over here with some sweet tires. Ooh. Okay, that's my car. No judgment, please. There's some friction between the road and the tires. That's what's causing the force needed to keep the car going around. This is R, and there's some force of friction. Okay, this is force of friction here. Okay, so we have our picture set up. Conceptually, what do we have? So we have an object going around with a constant speed around in a circle. We have uniform circular motion, UCM. And with that comes the fact that there is centripetal acceleration and therefore centripetal force. So that's associated with uniform circular motion. We also have to worry about friction. And with friction, that means we also have a normal force. And that almost certainly means that we have to deal with gravity. Most of these topics should hopefully be familiar by now. Okay, so equation-wise, in the context of uniform circular motion, the main one is that there is a centripetal acceleration equation which relates the two quantities that you have, a velocity and a radius. So speed squared over r, that's the centripetal acceleration. We have to deal with the fact that, we also have Newton's second law. I should have written that. Of course, whenever you have forces, you're probably dealing with Newton's second law. Newton's second law will relate the centripetal force to whatever other forces we have. The net force, there's only one, that's provided by the force of friction. The force of friction between the tires and the road, if you recall, that should be a static force. So the static force of friction between the tires and the road, that is what gives you your centripetal acceleration. So in other words, the net force is equal to ma. A is centripetal, and so what we have here is frictional force equal to the mass times v squared over r. Okay. Don't forget, from a previous unit, the frictional force that's static is less than or equal to a coefficient of static friction times the normal force. The normal force, because the car is on a level road, is equal and opposite to the force of gravity. The car presumably is not sinking into the ground or being launched into the air, so the normal force is equal in magnitude to the force of gravity, which is just mg. Okay? And what we're tasked with doing, we want the static coefficient of friction, at least what it must be at minimum to allow the car to go around and not slip. All right, so let's just try to go ahead and use Newton's second law, given all this information that we have. The static frictional force, we know it must be less than or equal to this combination, but at the very least, we know that if we're looking for the minimum value of mu s, we know that, let's assume that the frictional force is as big as it can possibly be. In other words, the static coefficient of friction times normal force, which is just mg, let's set that equal to the centripetal force, mv squared over r. Okay. We didn't make, at least I said, I didn't say that I was concerned about not being given a mass. I had assumed that the mass somehow wouldn't be relevant. Now we can see exactly how it ends up going away. we're looking to figure out what is the coefficient of friction that satisfies this equation. So mu s must apparently be equal to, or at least as big as, v squared over g times r. Do we have everything we need? 95 kilometers per hour for the speed. That's not a useful unit, but we can deal with that in a second. G we know is 9.8 meters per second squared, and r is 125 meters. So we're basically there. We just need to plug in the numbers. Let's do that really quick. V, 95 kilometers per hour times 10 to the 3 meters for every 1 kilometer. And we know that in 1 hour there are 3,600 seconds. And so this turns out to be 26.4 meters per second. With all those numbers put in place, we learn that mu s has to be 0.57 at least.